In this video, we will analyze a simply supported beam and find out the stress and deflection due to this distributed load of 5000 Newton. One end of this beam has pin support and the other end of this beam has roller support. The material for this beam is structural steel and the code for this beam is W12 into 12 into 96, which is a American standard wide flange beam. The dimension for this W beam is taken from a website engineering toolbox, and we will use these dimensions to create the geometry of the beam. The geometry of the beam was created in my earlier video. The link to that video is provided in the description. Next, open Ansys workbench, double click on the static structural, then right click on the geometry tab. Import the geometry from the folder in which you have saved the file. Next, double click on the model button. It will open Ansys mechanical. Now we will create the mesh. Click on this mesh tab and in the element size enter 10 mm for the element size and then click generate to generate the mesh. Now we will apply the boundary conditions. Click on the static structural and then click on this fix support button. We will apply the pin support at one end of this beam and then use right click to zoom into this section and then select this edge selection button to select this edge of the beam and then click apply. Then press this zoom to fit button and use the middle mouse button to rotate this beam. Then zoom into this area and select this edge, and then we will apply a displacement support at this edge. We will keep the X and Y components of this edge to be fixed and we will keep the Z component free. So for this we will enter X is equal to 0 and Y is equal to 0 and we will let the Z component equal to free. This will restrict this edge to not to move in the X and Y direction, but it can move in the Z direction. Press zoom to fit. It means that this edge can only move in Z direction and it cannot move in X and Y direction. In the next step, we will apply the force. Click on this force button. Go to this face selection tab and then click on this surface. Then click apply. We will define this force by components and our force is acting in the Y direction and with a negative sign because the force is downwards. So we will enter a force equal to negative 30,000. Then we will evaluate the results. Click on the solution tab. Then click on this deformation tab and click total. We will also evaluate the von Mises stress. Click on this equivalent von Mises stress and then click the solve button. Now the solution is complete. To have a better view, click on this edges button and then select no wireframe. We can see here the maximum deflection is at the center of the beam and which is equal to 1.21 millimeter. Then we will look at the equivalent stress. The equivalent stress is maximized at the sharp edges due to the stress concentration. If we zoom into this area, you can see the stress is maximum at the sharp edge which was fixed, but we expect the stress to be maximum at the center of the beam. So we probe the stress at the center of the beam by clicking this probe button and then click at the center of the beam, and the stress at the center of the beam is around 10.41 megapascal. Now we will compare these values of stress and total deformation with our hand calculations to validate our results. The maximum bending moment for the simply supported beam subjected to distributed load is found by using this equation, and the maximum bending moment is 22,500 Newton meter. With the help of this maximum bending moment, we can find out the bending stress, which is equal to 10.45 megapascal, which closely matches with our Ansys result. In this equation, C is equal to h by 2, where h is the height of this W beam and I is moment of inertia, and it is given in this table. This is the case of simply supported beam which is subjected to distributed load, and this equation will be used to find out the maximum deflection. So with the help of this equation, the maximum deformation is 1.21. So the maximum stress and maximum deflection are matched with our Ansys results. So our Ansys calculations have been validated. Thanks for watching this video.